First thing we talked about in the dynamics unit was Newton's first law. Summarized in one word as inertia. Okay, the tendency of an object to continue doing whatever it was doing in the absence of any unbalanced or net forces. Okay, the tendency of any object in the absence of net forces is to either remain stationary or continue traveling at a constant velocity along a straight line, obviously. Okay, so that's what inertia is. That's really all we need to know. That means, though, if we have a Newton's second law question that says an object is traveling at a constant velocity, it means the net force is 0. And that's the whole reason we go over Newton's first law, okay, is to be able to recognize situations where all the forces add up to 0. Okay? All right, then we spent the next 3 weeks talking about Newton's second law. All right, so Newton's second law in its simplest form, F net equals m times a. In a more realistic form, it is the vector sum of all forces. And that's usually where we ran into questions that were a little more challenging, when we had forces that were acting in different directions, forces that we had to calculate first and then put onto a free body diagram and a vector diagram and so on and so on. Okay, there were so many different situations that we went over in that unit that are governed by Newton's second law. Okay, we talked about just vectored forces. We talked about inclined planes. We talked about pulleys. We talked about sliding, boxes along tables against friction and all of that kind of stuff. There were all kinds of different situations. What we need to remember is that all of those situations can still be dealt with in the same way. Okay, that is, draw a free body diagram. Okay, then draw a vector diagram if necessary. Okay, and then calculate all possible forces. That could include net force. Sometimes net force was one of the forces that you could actually calculate given the data you had and you were looking for one of the other forces. Okay. And then the last thing was to solve. Okay. Effectively, all Newton's second law problems, no matter how involved they were, came down to those 4 steps. Okay, the free body diagram helped us to identify all the forces involved. The vector diagram helped us to figure out how they interacted with each other and produced the acceleration and net force. Okay, then we would calculate all of those forces so that we could actually mathematically get our final answer. Okay, everyone all right with that? Okay. So when I'm done kind of doing all the review, if there are specific types of Newton's second law problems that you would like to ask about, then I'll take those questions and we'll do as many as we need to do. Okay. All right. After Newton's second law, then we talked about Newton's third law. Okay, so obviously Newton's second law, guys, that's going to be some written response and some multiple choice. Okay, but the big marks are in the written response to do with Newton's second law. Okay, for Newton's first law, we're mostly looking at multiple choice kind of stuff to do with that. Okay, all right, for Newton's third law, okay, every action has an equal and opposite reaction. We did do a few fairly involved Newton's third law like problems. There won't be any of those on the final. Okay, like, like box 1 is pushing on box 2 is pushing on box 3, calculate the force of B on A. There's not gonna be anything like that on the final exam. Okay, but I mean, when it came right down to it, that was really just a Newton's second law question. All we had to remember that was when box A pushed on box B, box B would push back with the same amount of force. Okay, really that's all you have to remember about Newton's third law. So it'll be mostly multiple choice stuff to do with Newton's third law. Okay, the next thing we talked about was work energy theorem. All right, if you exert a force through a distance, you are going to change the energy of the object that you are exerting that force on. You are going to add mechanical energy to it. That mechanical energy could be in one of two forms. It could be kinetic, it could be potential, it could be one or just the other, or both. Okay, we dealt with all types of situations to do with changing the mechanical energy of an object. Okay, so what we have to remember, okay, is the work energy theorem mathematically stated is that work is a change in mechanical energy. Okay, that means work is mechanical energy final minus mechanical energy initial, which oftentimes came out like this. Okay, something along those lines. Probably don't need the brackets. I don't know why I put them in there, but okay, we're taking our final mechanical energy, we're subtracting our initial mechanical energy. Any difference between those is the work that was done on the object or by the object if it happens to be losing energy to something else. All right, that ringing a bell for people? Okay, like I said, most of the problems that we did to do with that just had to do with, like, okay, you're exerting this force, and the object's velocity, it changes by this much, and it goes this much higher. Calculate the distance over which the work was done, or something like that. Okay, they weren't terribly difficult calculations as long as we read the questions carefully. And then the law of conservation of mechanical energy. Okay, that was the last thing. So that's like roller coaster questions and things like that. Now, we did deal with conservation of mechanical energy in 2 units. There's conservation of mechanical energy in the written response part of your final exam. Could be one or the other or both. Okay, but it was in 2 units. Okay, so it's a pretty important concept. Expect to see it, okay, in the written response part of your final exam, along with work energy theorem. Okay, there's going to be some multiple choice stuff about work energy theorem, but not as much as there is written response. And then there's obviously going to be written response about the law of conservation of mechanical energy. Okay, so even though this was our longest unit, it actually had the least number of main topics, right? But there was just so many small concepts in each topic that it took us a long time to get through it. Okay, all right. What kinds of things do you guys want to see demonstrated or review or whatever from this unit? Okay, work energy theorem, all right. Sorry, I'm trying to figure out how exactly I want to do this question. It's just I'm stumping myself here. Okay, so we're going to be solving for force. Okay, we're going to say that the final speed up here is going to be okay, so the ramp is 20 meters long. At the bottom of the ramp, the box is moving at 2 meters per second. It's pushed all the way up the ramp, which is 20 meters long. Okay, and when it's at the top of the ramp, it is 6 meters higher than it was at the bottom and moving at 3.5 meters per second. I want to know how much force was used to push it there. Okay, what force did we have to use to push it there? All right, remembering that this is a work energy theorem question. The work done is equal to the change in the mechanical energy of the 20 kilogram box. Okay, I'll give you a couple minutes on that one, see if you can figure it out, and then I'll walk it through. All right, is the energy of the box changing as it goes up the ramp? Definitely. Okay, it has no potential energy at the bottom of the ramp and is only moving at 2 meters per second. At the top of the ramp, it has a considerable amount of potential energy and is going faster, so has more kinetic energy as well. So what I have to remember here, okay, is that work is the change in mechanical energy. That means the final mechanical energy minus the initial mechanical energy, okay, and that equals force times distance. So what we're going to have here is, okay, to calculate mechanical energy, I add potential energy to kinetic energy. Okay, and then I'm going to subtract final minus initial. So I'll have mghi plus 1/2 mvi squared. Okay, I'm trying to find force, and I know the distance over which this force acted. So all I have to do is manipulate for force. I have to divide this whole thing by d, and that'll give me force. All right, I can also realize that since this started at the bottom of the ramp, that I don't have any initial potential energy, and I can eliminate that formula completely. Okay, so all I have to do now is plug in my numbers. All right, so we'll have 20 kilograms times 9.81 times 6, that's our final potential energy, plus 1/2 times 20 times 3.5 squared, our final kinetic energy. And then we're going to subtract from that 1/2 times 20 times 2 squared. That was our initial kinetic energy. Okay. Divide that by 20 meters, the distance over which the work was done, and we'll have the force that was used to do that. Okay, so we've got 20 times 9.81 times 6 plus 0.5 times 20 times 3.5 squared minus 0.5 times 20 times 2 squared divided by 20. All right, so we had to use 63 newtons worth of force in order to make this happen. All right. That would be the total force used. F net would be the force needed to do the accelerating. Remember when we talked about that, we said it doesn't take a net force to change potential energy because you do that at a constant speed. The net force changes the kinetic energy because that's where the change in speed occurs. Right? Okay, any other questions on work energy theorem? Okay, what else do you want to see us go over? Josh? Roller coaster? Okay. Okay, so we've got this roller coaster. That's at the top of the first hill. We do not know how tall the first hill is, but we know it's moving at 6 meters per second when it's there. Okay, a little while later, it is much lower, only 8 meters above the bottom, and moving at 27 meters per second. So we need to calculate what the initial height of this roller coaster is. I'll give you a couple minutes to try it, and then I'll walk it through. Okay, is there any work being done in this question? No, there's no mention of any forces other than gravity. So this is a conservation of energy question, okay? Because there's no change in energy between the top of this hill and this hill. Okay, so we have initial energy equals final mechanical energy. So that'll be m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. And we are looking for this. We're looking for the initial height. Now, I never gave you the mass, so obviously it doesn't matter. Okay, we just need to get HI by itself. So I'm going to subtract 1/2 VI over to that side. So I'll have GHI equals GHF plus 1/2 VF squared minus 1/2 VI squared. And then I'm just going to divide that by G, and that'll leave me with H. Okay, so when I plug in my numbers, I'll have 9.81 times 8 plus 1/2 times 27 squared minus 1/2 times 6 squared divided by 9.81. Okay, and that'll give me my initial height. Okay, so the initial height of the roller coaster is 43 meters. Okay. All right, what else do we want to go over? Page? Pardon me? An elevator question. All right. Okay, so we have a rock thrown into the air. Its acceleration is 4.1 meters per second squared up. Okay, the mass of the rock is 1.7 kilograms. We're looking for the force that was used to throw it. Okay, now remembering that the request was for an elevator question, this is still an elevator question. Even though it doesn't say elevator, it says rock. Okay, free body diagram of the rock. What forces should I draw? Force of gravity. Okay, which we'll calculate right now. So we got 1.7 times 9.81. Okay, and what else? What other force needs to go on there? Or do any other forces need to go on there? Right, the force applied. Right, now the most common mistake in a question like this is to forget gravity. Right, but we didn't do that, so that's good. Right, so we have this applied force, but we don't know what it is. That's the one we're looking for. And we have the force of gravity. Is there something else I can calculate right now with the numbers I was given? I can calculate net force because I was given mass and acceleration. So I'm going to go F net equals m times a. That'll be 1.7 times 4.1 meters per second squared. All right, so my net force is 6.97 newtons. and it's up. All right, there's two ways to calculate net force. I've done one of them. What's the other way? The vector sum of all forces. So looking at my free body diagram says to me that net force is applied force plus the force of gravity. I'm looking for the applied force. So I'm going to subtract the force of gravity over here. So I've got F net minus the force of gravity equals the applied force. Okay, so that'll be 6.97 minus negative 16.677. Okay, why is it important that I made that negative? Yeah, gravity's pulling down. If I don't do that, I'm going to get that my applied force is really small, and there's no way that the rock could accelerate upwards if the applied force is smaller than gravity. Okay, all right, so when we do this, okay, so we'll go plus 16.677. All right, so our applied force is 24 newtons up. Okay. All right, what else do we want to go over? Okay, inclined plane, yep. Okay, that's what you have. A 70 Newton force is pulling that box up the ramp at a constant speed of 1.1 meters per second. I want to know what the force of friction is in this question. Okay, give you a couple minutes on that one. Okay, so with all inclined planes, what we have to remember here is that the net force is a combination of this small triangle inside. Obviously, gravity is pulling straight down on this box. Okay, the ramp is pushing straight outwards from the ramp with normal force, like so. Okay, gravity, like we said, pulling straight down. But the net force between these two forces is F parallel. Okay, and that is the force that does this, pulls the object down the ramp. This angle here is the same as the angle of incline. Now, given the information that I have, I should be able to calculate the force of gravity. Okay, 10 kilograms times 9.81, this is 98.1 newtons. All right, if I want to calculate F parallel will be the sine of 30 times the hypotenuse, which is gravity, so 98.1. That's going to be 49.05 newtons. So F parallel is 49.05 newtons. The question is asking what the force of friction is. Okay, so here's what we've got. The box, we're told the box is moving up the ramp. So which way is friction acting? Down the ramp. Friction always opposes, so we know that the force of friction is acting down the ramp. Okay, so that's helpful. We now know 2 out of the 3 forces that are contributing to the net force. All right, so my net force is F parallel plus the force of friction plus 70 newtons. Okay, the applied force up the ramp, whatever it happens to be. What's my net force? 0. Right, my net force is 0 because it says it was moving at a constant speed of 1.1 meters per second. So I know that 0 equals, okay, 49.05 plus the force of friction, which I don't know, plus 70 newtons. Now, I got to make this negative, because the 70 newtons is up the ramp and F parallel is down the ramp. So I do need to indicate there's different directions here using positives and negatives. So if I want to solve for FF, I just need to bring these other 2 forces over to this side by subtracting them both. Okay, so I'm going to have negative 70, okay, or sorry, I'm going to have negative 49.05, okay, minus 70 newtons, okay, and that should give me another negative number, okay, and that'll give us our force of, sorry, positive, because that's going to be minus a negative, okay, minus 70, that'll give me a negative number, okay, and I'll have my force of friction going down the ramp, okay, so we'll have 49.05 minus 70, okay, and we got that the force of friction is negative 21 newtons. All right. Everybody all right with that? Okay. All right. What else? Ken? I was solving for force of friction. I left it over here. That's what, it came out negative when I did it. So yes, I would. Okay. All right. Well, if there's no more questions, then let's get back to work on the review package. Hopefully more questions will come up. Okay, obviously, guys, like the unit or the final exam, I tried my best to make sure that the units were equally represented in terms of points, but they're not perfectly represented equally in terms of points. So understand that probably kinematics and dynamics ended up being weighted a little heavier. All right, so there'll be more stuff between unit 1 and 2 than there will be on units 3 and 4. Okay, I would say if one unit got shortchanged more than any other, it's unit 4. Because, well, that's the most recent one. You're having a unit exam on it on Thursday, so expect that there'll be less of that on the final. All right, so let's get to work on the review stuff, and hopefully some more questions will come up. Happy to answer them when you have them. Yeah. All right, if I'm looking at this question, okay, the first thing I want to do is add on all the forces that I know are there, and I want to eliminate the angled force by just finding its horizontal and vertical components. Okay, it'll simplify what I need to do. All right, so obviously one of the forces acting in this situation is the force of gravity, which will be 196.2 newtons. Okay, I'm going to have some normal force acting upwards. It's not going to be 196.2 newtons, however. Why not? Right, the vertical component of this 150 Newton force is going to be bearing some of the weight of this box. Okay, so we need to find this force vertical, right, by going sine of 30 times 150. So this force vertical is 75 newtons. All right, so now that we know that, okay, what I'm going to do is just move it over to here. Okay, it's a little long, but okay. Okay, so it's there. And then I'm going to find the horizontal component of this 150 Newton force by going cos of 30, because I'm finding the adjacent side. So cos of 30 times 150 newtons. All right, so that side's 129.904. Newtons. That now allows me to get rid of this. Okay, I now have the components of that force that are acting along the table. What force am I still missing? Friction. Okay, so these are all of the forces that are acting. Now, one of the things I need to know about the vertical part of this is that the object is not moving vertically. So what is the net force vertically? 0. right? So that means that the forces up plus the forces down have to equal 0. So I'm just going to go 196.2 minus 75, and that'll tell me what the force normal is. Everyone okay with that? Yeah. Okay, so we're looking at 121.2 newtons for our normal force. All right, can I use the normal force to get the force of friction? Yes, and that's the next thing I have to do. Force of friction equals mu times the normal force, and they gave me mu, so 0.275 times 121.2. All right, so we're looking at a force of friction of 33.33 newtons. All right, so now I've calculated all the involved forces, which is one of the steps we talked about, okay, that we want to do. We drew the free body diagram, we took care of the vector stuff, now we've calculated all the involved forces. Now we need to calculate what? If I want to find the acceleration I need, net force. Okay, so net force is going to be the vector sum of all forces. I'm going to help myself out here by eliminating 3 forces. I don't need to add that one, or that one, because I already know they add up to 0. Okay, so the only 2 forces I'm worried about are the force forward and the force backwards. All right, so F net will simply be 129.904 minus 33.33. Actually, 9038106, because I should keep all of my decimals, 33.33. All right, so we're looking at a net force of 96.57 newtons. I divide that by my mass, 20 kilograms. And this thing is accelerating along the table in a forward direction at 4.8 meters per second squared. Okay, that's a fairly involved question, but you had one exactly like that on your unit exam. Okay, it's time consuming, but it tests about 3 or 4 things to do with Newton's second law. Okay. All right, what else? You? A roller coaster question? Okay. I think I have one on here already. I do. Okay, so let's just do this. Okay, so a hanging sign question is a static question, right? If it's static, that means the net force right away is what? 0. Okay, so this circle here that's being held up by these 2 cables has a mass of, let's say, just for having a nice round number, 100 kilograms. Okay, angle between these 2 cables we'll say is 120 degrees, and we want to find the tension in each cable because they'll be identical. Okay, the tension in each cable will be the same. So we're looking for the tension in the cable. So in a question like this, what's the forces, or what are the forces acting? Gravity. All right, so we got force of gravity, 981 newtons. Okay, and what is keeping this thing from falling? The tension in the cables, specifically the vertical component of the tension in each cable. All right, so we have so we have this triangle here. Okay, this angle was 120. Now that I've split it, this angle here is now 60 degrees. Everybody all right with that? Okay, so the tension that I'm looking for is now the hypotenuse of that triangle. But I still need one more side. I have an angle, but I don't have a side. Okay, which one of these sides can I find? The vertical one. How big is the vertical side for each cable? It's the same, but how big is it? Half of this. There's 2 cables. That's the trick to a question like this, right? Each cable's holding half of this 981. Okay, so this side here is 490.5 newtons for this cable, and then there'd be a similar triangle over here that would have a vertical component of 490.5. Now that I have that, okay, I have the adjacent side, and I'm looking for the hypotenuse. Okay, so the cos of 60 degrees, okay, equals 490.5, the adjacent side, okay, over the hypotenuse. Okay, so I'm just going to go hypotenuse equals 490.5 divided by the cos of 60, which I believe will make that 981 newtons. Pretty sure. Yeah. You had exactly one like that on your assignment, right? And people didn't like the fact that the number came out to the same as the weight of the sign, okay? And people were second guessing that they had done it wrong somehow. Okay? It was just because I picked that lousy angle.
What about one like the cable's like straight up?
If the cable's straight out, okay, so you had one like this on your assignment as well. Okay, suspended by two cables, one cable being horizontal. Okay, so we'll just say that we'll just say it's a 100 kilogram sign. Right, this angle here can be, I don't know, 40 degrees or something. Okay, so we got a 40-degree angle there on that cable. Okay, and we've got a 100 kilogram sign, which means the force of gravity acting down is again 981 newtons. No, because then we would have to know how hard it's pushing against the wall, how hard the wall is pushing back, all of that kind of stuff. It would, yeah, it would throw a monkey wrench in for sure. Okay, so we got cable B and we got cable A. This question would probably be asking, what's the tension in cable B? All right, now here's what we have to realize about cable B. Cable B can only pull horizontally. So is it offsetting any of that 981 newtons? No. Which cable is holding the 981? Cable A. What part of cable A is holding the 981? The vertical part. Okay, so cable A has a vertical component and a horizontal component. Its horizontal component is pulling against cable B. Its vertical component is pulling against gravity, and we know that it's 981 newtons. What's the net force in this question? 0. That's an important thing to recognize as well. All right, so if I know one side of this triangle, and I know that this side of A is equal to the tension in B, I need to find this side here for cable A, and then I'll know the tension for cable B. All right, so all I have to do is trigonometry here. It'll be tan, because I'm using the opposite and adjacent sides. So the tan of 40 degrees is equal to the opposite side, which is what I'm looking for, divided by 981. So all I have to do is go tan of 40 times 981, and I'll have the tension in cable B. All right, so we're looking at a tension in cable B of 823 newtons. Actually, we only have, no, we have two significant figures, 8.2 times 10 to the 2 newtons. And I wouldn't have to put a direction on that because it's tension. Okay, what else? Okay, combination of unit 1, unit 2 question would probably involve doing a Newton's second law problem, and then at the end, and then having to use like VI, VF to calculate A in order to get net force. So it's really nothing like overly new. It would just add in that you'd have to do an acceleration calculation first using that data. So might look something like this. And we'll say it's a 1,500 kilogram car. This is pretty simplistic, but it's what I can think of just off the top of my head. Okay, so sorry, I would need one more number here. I would need the distance, so or time. let's just say it skids to a stop using 1200 newtons worth of frictional force in, let's say, in 60 meters. I don't know. I'm just making up numbers here. This might not work. Okay. So if I know the mass of the car and I know that the force of friction is 1200 newtons, this car is skidding to a stop, and I didn't write, but it's along a level road. What's the net force? Okay, it's a level road, and I'm skidding. The engine's not pulling anymore. The only force that's stopping me is friction. So the net force is, nope, 1200 newtons. Okay, you use 1200 newtons of frictional force. When you skid to a stop or you run out of gas and coast to a stop, what's stopping you is friction. Okay, friction is the only force acting on you unless you're going uphill. Okay, this is a level road, right? So our net force is mass times acceleration, and we're looking for the acceleration of the car because we're looking for how fast the car was traveling initially. So acceleration will be F net divided by M, so that'll be 1200 divided by 1500. It's not a very big acceleration, it's a bit unrealistic, I guess. 1200 divided by 1500. Okay, so our acceleration is 0.8 meters per second squared. That's negative because it's slowing down. Okay, now that I have that, then I'm going to use this one, VF squared equals VI squared plus 2AD to solve for my initial speed. So that'll be VF squared minus 2AD square rooted equals VI. So we'll have 0 squared minus 2 times negative 0.8 times 60 meters. All right, so the car was moving at 9.8 meters per second before it slammed on the brakes. That's what happens when you pick numbers out of your head. It doesn't really make sense, but that's the number. Okay, that would be a question that would involve something from Unit 1 and something from Unit 2. Yeah. Okay, what else? You guys did a much better job of filling up the period with questions than period 2 did. We did yesterday. Yeah, it's in the podcast, which didn't post for some reason, but it's posted now. Okay, so if you weren't here yesterday, then check that one out. Okay. All right, I'll give you the rest of the time here to work on that review package. Hopefully another couple of questions will come up. We got about another, 5 or 6 minutes here, okay, for you guys to work. All right.